Let's take a look at some modeling here, some nonlinear modeling, meaning in this particular case, we're going to look at a quadratic model, which is not a straight line. So let's first discuss the shape of a quadratic model, what circumstance you might use it. So the shape of a quadratic model is what's called a parabola, okay? A parabola. And what characteristic does a parabola have? Well, it has this idea that it goes up. It goes up and then back down. So it could rise, hit a top point and come back down, or vice versa. It could drop, hit a low point and rebound and come back up. So it could be a shape like this, or it could be a shape like this. Okay? So those are quadratic models. That's the shape of a quadratic model. So things that exhibit this type of behavior might be modeled with a quadratic function. Okay, so what does the function look like? So typically, not typically, but a quadratic function or a quadratic model has x squared, okay? So not x to the first power, well, it could have x to the first power, but it has an x squared somewhere, and it does not have an x cubed or anything higher. So the highest power of x is x squared, okay? So let's take a look at an example of something that might exhibit this type of behavior. We'll look at an equation to represent this sort of behavior, and then we'll use it to make predictions about future behavior. Okay? So let's look at an example. So one type of example might be when you hit a baseball, the angle that it comes off the bat, you can imagine the lower the angle is, the ball might travel less distance. And as the angle goes up, the ball might travel further. Of course, there's bat speed, all kinds of things that factor into this. We're trying to keep it simple though. But then you can imagine a low angle could result in a low distance traveled. As the angle rises, the distance could go further. And then once the angle gets so steep, it's going to start coming back and not traveling as far. Okay, so an example might be seeing how the hit angle of a baseball, how does that impact the horizontal distance that the baseball travels? Okay, so if we were to look at a graph of what this might look like, just to get an idea, we'd get what's called a scatter plot. Maybe data is gathered for hit angles at 10 degrees, how far they went, and then that could be average. So on your x-axis, you could have your hit angle. And let's assume that's in degrees. Okay? And then on your y-axis, you could have your horizontal distance. And let's assume that's in feet. Okay? And so you can imagine if you have a low hit angle, so if this is 0, if you have a low hit angle or 0 degree angle, you're not going to travel any horizontal distance. But as your hit angle goes up, so does your horizontal distance until you reach like this angle of maximum distance, which maybe is right here. And then after you reach that angle of maximum distance, your distance might start to come back down like this. Okay? And so you can see this scatter plot of data indicates that, well, it seems like the distance traveled maxes out somewhere and then it starts to come back down. And so this is a great example of when you might want to use a quadratic model. Now, in mathematics, what you can do is, and we're not going to focus on how to do this part of it, you can do what's called a regression, where you actually, now you've got these individual points, you try to find a curve or a function that you can use to approximate those points, okay? So let's talk about how you might do that. So we'll look at the type of model we'll use, and in this case it's a quadratic model. On a graphing device, you might use a feature called quadratic regression, which is abbreviated maybe as quad reg, and we're not going to do that part, okay? So I want to emphasize, I'm not teaching you how to do regression in this video. I'm showing you how you might use regression if you have the results of it, okay? So you might use a quadratic regression on some sort of graphing device. And what that's going to do is it's going to give you that function that we talked about. The function that mimics this curve. What's the equation for that function? So it's going to give you an equation for a quadratic model. The equation is going to be a times x squared plus b times x plus c. And so you can see this is quadratic because x is squared. Now a, b, and c are numbers. The values of a, b, and c change depending on this whatever the particular curve is. You can imagine if your curve were steeper or narrower or shorter, a, b, and c would change, okay? But if you're using a graphing device, it would give you this equation, and then it would tell you the values of a, b, and c for this particular model. You could input your data. It's going to generate a function with the values of a, b, and c given. So I've got those written down here that we're going to work with. So let's say that a is negative 0.1737 141137. Okay? And then B is 14.5211 7133. And finally, C is negative 21.8977 4466. And so now we have this function for that curve, okay? And so what I will do at this point, this is the feature you might use on a graphing device to generate this function based on the points you have there. So now let me reinterpret this how we might write it on paper. We could say, okay, so the function for this curve, is y equals a, which is all of this. So a times x squared, I'm going to write it out in a second, plus b times x plus c. So I'm going to pause the video, write all of that out, and you can do the same if you're taking notes, and I'll come right back to you. Okay, so I rewrote our function with ax squared plus bx plus c. Notice that c was negative, so it turns into a minus. Now, we can use this function to determine what hit angles will give us a horizontal distance. So we could ask the question now, how far will a ball travel that is hit at 10 degrees? How far will a ball travel that is hit at 10 degrees based on this model? So the way you would figure that out is you look at how this equation is set up, and x here represents the hit angle. So in this case, the 10 degrees is your x value. So we're going to use x equals 10, and it's asking how far will it travel. That's going to be our y value, okay? So we're literally going to come up here to our model. We're going to replace the x's with 10. So this will be times 10 squared. This will be times not x, but times 10. And we're going to type all of this into our calculator, and we're going to see what y is, and then that will be our answer. I've already typed it in, and it appears that, as long as I don't have any typos in my calculator, it appears that y equals, let's say approximately equals, y is approximately 106. And in this case, y is measured in feet, so y is approximately 106 feet. So if a ball is hit at 10 degrees, it's only going to travel about 106 feet based on this particular model, this regression that we got from a graphing device. Now let's change the angle. Let's maybe look at 45 degrees. At 45 degrees. So now we just change our x value to be 45. And on my calculator, I can still see what I just typed. I typed all of this at once. So what I'm going to do now is I'm going to go back and I'm going to change these 10s. So I'm going to hit my up arrow so I can reuse what I typed. And I'm going to use my arrows to scroll over to the 10, and I'm going to delete the 10 and change it to 45. Lots of ways to leverage the use of your calculator here. It's not terribly fast, but it's much faster than retyping the whole thing and risking some sort of typo. Okay, so whenever I plugged in 45 for my hit angle, the y value, the horizontal distance, is about 280 feet. Okay, so you can see that at a 45 degree hit angle is traveling much further than it did at a 10 degree hit angle. And just for good measure, let's do one more where we check it at a bigger angle, maybe a 70 degree angle. A 70 degree angle, which means that we're going to plug in 70 for x into the same function. So again, just go now and change all the 45s that you had to 70s. Now I'm only recording myself doing it because I expect that you're probably checking these out for yourself as well. If not, I assume you'll fast forward through these slow parts of the video. So it looks like in that case we get about 143 feet. So you can see at 10 degrees you had a low horizontal distance, at 45 degrees you had a pretty high horizontal distance, and at 70 degrees you had a low horizontal distance again. So that exhibits this quadratic model type of behavior.